Hello dear students, welcome you all. In this lecture, I am going to discuss about the semi-empirical mass formula of atomic nucleus, right? This formula was given by Bethe and C.F. von Bisseck in 1935, right? Bethe and Carl Friedrich von Weizsäcker in 1935. So sometime we also call it as a Bethe-Weizsäcker formula, right? Now this formula is semi-empirical in nature. Semi-empirical means, we know very well, empirical means experimental. So it means this formula is based on some experimental evidences as well as some theoretical predictions, theoretical aspects. So it is a mixture of theoretical as well as some experimental facts. And this formula is a first, step or first effort to express the mass of the atomic nucleus in terms of its winding energy, right? We know very well that the mass of the atomic nucleus, if I write it as MAZ, then it will be equal to Z time mass of proton plus A minus Z mass of neutron. Now, if I equate these two quantities, then I will found that this quantity is more than this by some amount. We call it that amount as mass defect, right? And the energy corresponding to that mass defect is called winding energy. So if I subtract that winding energy here and I divide it by c square, now it becomes mass. Now these two sides become exactly equal, right? Now this is the expression for the mass of a given atomic nucleus that has mass number A and atomic number Z, right? It expresses mass in terms of mass of protons, mass of neutrons and the winding energy, right? In some books you may found c square missing. You will only find that it is equal to ZMP plus A minus ZMN minus V. So don't get confused. They are just writing V as the mass corresponding to the winding energy, right? So now this is the peak of an atom. You can see here. Here we have atomic nucleus. It is shown here. It contains proton and neutrons which are packed tightly inside the spherical volume, right? That we call nucleus. And this is the peak of atomic nucleus. You can see here. Now, as I told you that this formula is a first effort, first step to calculate the mass of the atomic nucleus in terms of winding energy. Although we don't have exact experimental results or theoretical results, but it is a rough approximation, and you will wonder that this formula was very significant in explaining the mass of many atomic nuclei that exist in nature, and it is also capable of successfully explaining the phenomenon of nuclear fission, right? The splitting of a heavy nucleus into two lighter nuclei, right? So now I am going to discuss about this approximation in details, because we know very well about these two terms. Let call it this equation as a equation number 1, right? Now this is atom and this is the atomic nucleus. It contains, you can see, protons as well as neutrons, right? In a very small a volume of the order that has a dimension of the order of 10 raised to power minus 15 meter, right? Now as I told you that the mass of the atomic nucleus can be expressed in terms of the winding energy. So according to semi-empirical mass formula, this winding energy have different contributions, and according to this formula we are considering only 5 contributions. These are the volume energy term, right? Surface energy term, right? Coulomb energy term, right? Asymmetry energy term and pairing energy terms. So we have a total 5 contributions in this winding energy, right? Let this is equation number 2. In this equation, right? Now I'm going to discuss all these 5 terms one by one. You can see here these 5 contributions are shown in terms of peak here. This is the first one, this is the second one, this is the third one, this is the fourth one, and this is the fifth one. I'm coming to the first one, that is volume energy term, right? BV. Now this term in the winding energy arise because of the tendency of the nucleons to form bonds and stay together. We know very well that the nucleons means neutron and protons, they stay inside the atomic nucleus because of the strong nuclear forces. Like this is a proton and this is a neutron. So these neutrons and protons are held together inside the nucleus by strong nuclear forces. I mean, they are attracting each other because of this nuclear force. So suppose I have 2 nucleons, they can be 2 protons or 2 neutrons. So as these 2 particles are bonded with each other, whether they are 2 protons or 2 neutrons, suppose these are 2 particles, whether they are neutron proton or proton proton or neutron neutron, let they are bonded with each other and they have the bond energy U, right? So the bond energy means binding energy is shared with these 2 particles. So each nucleon will have binding energy or bond energy U by 2. Now if I have a arrangement in which the spherical bodies are packed closely inside a lowest possible volume, right? Suppose you can see here, this is the case where I have some spherical balls, you can take the case, and they are packed tightly inside the lowest possible volume. In that case, each sphere, right, if I take the case of this one, it will have 12 neighbors to it when there is very close packing, right? Then in that case, every sphere will be surrounded by 12 spheres. It means this bond energy will be shared with the 12 neighbors. So it will becomes 6U, right? Now if a nucleus have a number of nucleons, then the total binding energy, that will be, right, we call it as V volume, that will be equal to how much? 6U into A. Now we know very well 6 and U, they are constant, fixed. So V volume energy directly proportional to A, right? Or if I remove the proportionality sign, then it will become V is equal to is equal to A volume energy constant into A. Now this is the volume energy term. Now why we are calling it as volume energy term? Although it is associated with the winding of the nucleons, we call it as volume energy because just like the volume of the atomic nucleus, we know V directly proportional to A, volume is also proportional to A, this term is also proportional to A, right? We have remembered in the first unit that volume of the nucleus is directly proportional to the mass number. So this term, energy term, is also proportional to the mass number. So that's why we are calling it as a volume energy term. One more thing is that this term is taken as a positive. Why we are taking it as positive? Because this term is increasing the stability of the nucleus. It is binding the nucleons together inside the nucleus, right? So we are taking binding. Binding means binding the nucleons together inside the nucleus, right? So this is positive, right? Now I am coming to the second term. This is the first one. Now I am coming to the second one, surface energy term. Right. This was the first one, volume energy term. Now surface energy term. Now recall the first calculation here. Here we have assumed that each of the nucleon inside the nucleus is surrounded by 12 neighbors. But rethink about it. Those nucleons which are present on the surface like this you can see here, this one, these nucleons will not have exactly 12 neighbors, but they will have less number of neighbors because they are not present inside the nucleus, they are present on the surface. So obviously they will have less number of nucleon in the surrounding. So the binding energy that we calculated here, it is overestimated, right? It is overestimated. We actually multiplied with A, but it is wrong, right? All the nucleons don't have 12 neighbors. So we have to take the adjustment of this overestimation. So this adjustment is called surface energy term. I mean, we have to decrease the energy corresponding to the surface nucleons, right? And then we will get the correct winding energy. So this surface energy term, we know very well, the nucleon on the surface of the sphere, that is atomic nucleus, it depends upon the surface area. We know very well that the surface area of the sphere is equal to 4 pi r square, right? So it means this energy, surface energy, directly proportional to this surface area, because the number of nucleon will depend upon this factor. So I can put, now we know very well r is equal to r naught a power 1 by 3. If I put it here, I will get Bs directly proportional to 4 pi r naught square into a power 2 by 3. So I can further simplify it. So I can write Bs directly proportional to a power 2 by 3. Or if I remove the proportionality sign, then I will write it as Bs is equal to negative As. This is the constant corresponds to the surface energy, a power 2 by 3. So this is the term corresponding to the surface energy that is have to be subtracted from the first term. So that's why we are taking it as a negative, right? Because it has to be decreased from the first term that is responsible for winding the nucleon, right? So this is the second term. Let this is equation number 3, right? This was equation number 1, this was 2, this was 3, and this is 4. This is equation number 4. Now I am going to the next one, third one, that is Coulomb energy term. Now we know very well that the atomic nucleus contains neutrons as well as protons, right? We know very well that the protons are positively charged particles, so they are going to repel each other. You can see here in the Coulomb energy term, these are proton, they have taken these red circles as protons. I have written here as a red circle as neutron, so don't confuse with it. It is our own choice. So they have taken the red circles as protons. So you can see here the proton are repelling each other. So due to the repulsion of protons with each other, right, now the atomic nucleus is going to be unstable. I mean, this effect of the repulsion is going to decrease the binding energy of the atomic nucleus. It is going to decrease the stability of the atomic nucleus. So we have to take this term also into the consideration, right? And we call this term as a Coulomb energy term. You can see here once again I am showing you that these all protons, they are protons, P, right? P, they are repelling each other, right? So due to the repulsion, the stability of the nucleus is decreasing, right? So now in Coulomb energy term, we know very well that the potential energy, right, between the two protons that are separated by a distance r, that is equal to E square upon 4 pi epsilon naught into r. This is the potential energy between the two protons, right? Now we know very well as there are z protons, so that z protons will have z into z minus 1 divided by 2 pair of protons inside the atomic nucleus. We are considering the atomic nucleus that has z protons and a mass number and a minus z neutrons. This is the case of this nucleus. So here I told you that the repulsive potential energy, right, the between the two protons is equal to this. So as we have to calculate the number of total pairs of protons inside the nucleus. So the nucleus has z number of protons. So the total number of pairs that are formed inside the nucleus of z protons, that will be equal to z into z minus 1 divided by 2. So the total repulsive this potential energy, that will be equal to now z into z minus 1 by 2 into e square upon 4 pi epsilon naught r average. Now here I wrote r average. R average is the average distance that I took between the different pairs of protons, right? Here we have taken only 2 protons, but now we are considering all the protons. So I am taking the average distance, right? So I can further simplify it, right? Now we know very well that the r average will directly or indirectly depend upon the value of the radius of the atomic nucleus. So I can write that this energy V Coulomb, right, this B Coulomb energy will be directly proportional to the z into z minus 1, right, divided by r, yes, right, and r is equal to what? R naught a power 1 by 3, right? R naught is again constant, so I can drop it. So I can write that it depend upon a power 1 by 3, because if you put 2 is constant, 4 is constant, pi, epsilon naught, e, all these are constants, and in place of r I can write z into z minus 1 divided by 8 pi epsilon naught e square upon r, right? So then I eliminate all the constant, I took the proportionality sign, it becomes z into z minus 1 divided by this, right? Now if I remove the proportionality sign, V Coulomb energy is equal to minus a Coulomb, right, into z minus 1 divided by a power 1 by 3. So this is the Coulomb energy term. Now again, what is the meaning of this negative sign? You know very well that negative sign means this energy term is going to reduce the stability of the nucleus and it is decreasing the binding energy of the nucleus. So that's why it is negative, right? And I'm going to name it as equation number 5. Minus AC z into z minus 1 divided by a power 1 by 3, right? Now I'm coming to the fourth term, asymmetry. We know very well that the lighter nuclei has a n is equal to z. This is very important feature. We have learned it in the first unit also, but as we proceed toward the heavy nuclei, the number of neutrons start increasing in order to adjust the increasing repulsive forces between the protons. But when the number of neutrons start increasing rapidly, right, then they are also becoming a problem for the nuclear forces. Why? Because the size of the atomic nucleus is also increasing, right? So these excess neutrons, right, you can see here we have a neutron pairs, they are all paired, right? I mean equal, if this is neutron and this is proton, so you can see all these are paired. These are the left out neutrons, right? These are not getting paired, means they are excess neutrons in addition to the number of protons. Now these excess neutrons, they are going to decrease the stability of the nucleus. Why? Because due to the increase in these neutrons, the size of the nucleus is also increasing. Although these neutrons are also increasing the attractive force between the nucleons, that is strong nuclear force, but the size is also increasing, that is also matter of concern. So that's why we are calling that these excess neutron will reduce the stability of the nucleus, decrease the winding energy of the nucleus, and this we call this term as asymmetry energy. You can see here I'm coming to the, this was the Coulomb energy, I'm coming to the asymmetry energy. This was the fourth one. Asymmetry energy term. You can see here, when n is equal to z, both are equally distributed in their respective cells, right, up to this energy level, right? We don't have excess neutrons. What this is the case when n is greater than z. You can see we have 4 excess neutrons. Now these excess neutrons are going to pose a big threat for the stability of a nucleus, and we have to also make the contribution of this asymmetry energy in the winding energy term. Now this energy, asymmetry energy, this depend upon 2 factors. The one thing is we call it as V asymmetry. It is directly proportional to one factor, that is the excess number of neutrons, and the second factor is when we have excess number of neutrons, they are also increasing the volume or size. So we will also make it into consideration the fractional volume n minus z divided by a in which these excess neutrons are present. So these are the 2 factors on which this asymmetry energy depend. One is the excess number of neutron, and the second is the fraction of nuclear volume, right? Fraction of nuclear volume can be calculated. Total volume depend upon A, and the volume in which these excess neutron present, it depend upon n minus z, right? So I was saying that this fractional volume can be calculated by dividing the volume of the excess neutrons divided by the total volume of the atomic nucleus. We know very well that total volume depend upon the value of A, and the excess neutrons volume will depend upon the number of excess neutrons. That's why this factor is taken into consideration here. Now I can write it as B asymmetry energy directly proportional to n minus z whole term square. We'll take that multiplied here, right, divided by A, right? Now we know n is equal to A minus z, so I can write this term B asymmetry directly proportional to A minus 2z whole square divided by A, because n is equal to A minus z, right? Now if I remove the proportionality sign, then this factor will become B asymmetry energy is equal to negative A asymmetry into A minus 2z whole term square divided by A, right? Again this term is taken as negative, I told you, because it is reducing the stability of the atomic nucleus, right? So this is equation number 5, this is equation number 6. Now I am coming to the last term, that is 5th one, pairing energy term. We know very well, we have learned in the first unit that the most of the nuclei that we see in the nature, they are even in their form. Even means even number of protons and even number of neutrons, right? And the odd nuclei are rare in the nature. It means the nucleons has tendency to get paired. Those nuclei which are having neutron and proton paired, right? Paired means even number. They are more stable as compared to the nuclei which have unpaired either neutrons or protons. I told you that even nuclei are most stable and odd are least stable. Even odd and odd even are intermediary, right? But the most stable are even, right? And the least stable are odd. It means the nucleons have a strong tendency, both neutron and proton, to get paired. You can see here these protons are paired, right? Paired. So now because of this pairing, their winding energy is more. But if I have excess, for example, one neutron is here and one proton is here, now it is odd. Odd means both neutron and protons are unpaired. That nuclei will be the least stable. But if I have suppose this is even and this is odd, or this is even and this is odd, in that case the stability is intermediate. So this term has been taken into consideration in order to make the this experimentally observed fact into the consideration. So we consider this term B5, we call this term as a pairing energy term, and this is equal to plus minus delta, right, or a 0, right. So we wrote this term as plus minus A pairing energy divided by, it is found that this term depend upon it, this result is directly taken from experimental observed facts, and here this is the constant. So as I told you that this term is taken as this comma, not comma now, this is enough. So this term plus minus, why I took plus minus, it can be plus, it can be minus, it is plus A P divided by A raised to power 3 by 4 for even, right, nuclei. It is equal to negative this factor for odd, and it is equal to 0 for even odd or odd even, right. So this term BP is equal to plus minus A pairing divided by A power 3 by 4. This is the pairing energy term. I told you that this term has been taken directly from the experimental observed facts, right, and the dependence on A power 3 by 4 is also taken directly. I told you in the beginning that some facts and some terms in this formula are taken from the experimentally observed facts, and some terms are theoretical predictions. Now I have all 5 terms, right, pairing energy term, asymmetry energy term, right, Coulomb energy term, and surface energy term, and volume energy term. So I can now write down the formula here. By combining all these terms, I can write this formula as first of all I am writing the winding energy, that is equal to A volume into A minus A surface into A power 2 by 3 minus A Coulomb into Z minus 1 divided by A power 1 by 3 minus A asymmetry into A minus 2Z square upon A plus minus A pairing divided by A power 3 by 4. So this is the expression for the winding energy that I have written here, right. Now if I put this expression in equation number 1, then I will get the formula for the total mass of the atomic nucleus, right. So I can write it here. Now mass of atom MaZ, that is equal to Z time mass of proton plus A minus Z mass of neutron minus B have now B upon C square, so 1 upon C square into A volume energy term A minus A symmetry energy term constant into A power 2 by 3 minus A Coulomb energy term into Z into Z minus 1 divided by A power 1 by 3 minus A asymmetry energy term into A minus 2Z whole square divided by A, and then plus minus A pairing energy divided by A power 3 by 4. So this is the required formula that we call as a semi-empirical mass formula, right. This formula expresses the total mass of the atomic nucleus, you can see here, in terms of the mass of proton, mass of neutrons, and the mass corresponding to the various contributions in the winding energy, right. If I took this negative inside, all the signs will get changed, and in some books you can found that this C is missing, so it is understood that these terms are the mass corresponding to the binding energy. So in that case, this formula will get changed. Now I am telling you about the value of all these constants, which has been taken directly from the experimentally observed fact. It is found that the AB, right, volume energy term constant, it is equal to 14 mega electron volt. Similarly, the next one, A, surface energy 13 mega electron volt. Similarly, you will have the next one, that is Coulomb energy, A Coulomb 0.60 approximately mega electron volt. Similarly, you will have a Asymmetry energy term, that is equal to 19 mega electron volt, and the last one is a pairing energy term, A pairing energy, that will be equal to 33.5 mega electron volt. So all these are the constants that we have to remember, because in the coming topics we can be asked to solve the numerical problems based on this formula. So in that formula, these constants will be utilized in addition to the value of A and Z, right? So according to that, we can calculate the mass of any atomic nucleus, right? If I know the value AV 14, 13.60, 19, and then 33.5 mega electron volt. So this is all about the semi-empirical mass formula. I think I forget to tell you in the beginning one thing, that was the a few assumptions made by Hans Bethe and C.F. Sec, right? Before driving this formula, they have made some assumptions. So these assumptions, I am counting them one by one here. The first assumption was that the nuclear density is constant. I mean, the nuclear matter is distributed uniformly inside the nucleus. The second thing is these neutrons and protons, they are fermions and they occupy separate energy levels as per the rule of Pauli's exclusion principle. I mean, only two nucleon you can see here, they can enter in the separate respective. I mean, the neutron will have different cells, protons will have different cells. We have explained it from the knowledge of quantum mechanics. This was the second assumption. The third one was the nuclear forces are charge independent. We know very well, we have gone through it in the first unit, and these are short range forces. They saturate up to certain nucleons, right? And we have also considered that there is a tight packing of the nucleons inside the atomic nucleus, right? So this is all about the semi-empirical mass formula. It is very important formula in the nuclear physics, that is used for calculating the mass of different atomic nuclei. It is used for explaining the nuclear fission. Once again, I am going to all these terms: volume energy term plus AVA, right? Then surface energy term minus AS A power 2 by 3, Coulomb energy term minus AC Z into Z minus 1 divided by A power 1 by 3, asymmetry energy term, that is equal to minus A asymmetry A minus 2Z square divided by A, and then pairing energy term, that is plus minus A pairing divided by A power 3 by 2. So this is all about it. In the next lecture, I will discuss the graphs corresponding to these different terms and the variation of the total winding energy with mass number, right? So thank you very much.